When we look at molecules drawn on a page, they seem so, well, static, like tiny frozen sculptures. But the truth is, they're more like bustling cities, alive with activity, all driven by this invisible, high-speed dance of electrons. So in this explainer, we're going to pull back the curtain on that hidden world and learn how to actually map the forces that make chemistry, happen.
To really get any chemical reaction, you have to understand that there are these two layers to reality. First, on the left, you've got static matter. These are the atoms themselves and the super strong single bonds, we call them sigma bonds, that act like molecular glue, holding the whole skeleton together. Think of this as the stage. But the real show, the action, is what's happening on the right, electronic motion. This is the constant, invisible flow of electrons that decides everything about how a molecule is going to behave. So our job right now is to learn the visual language that chemists invented to track all that motion.
All right, so how in the world do we actually see something that's invisible? Well, it turns out we use a tool that's both really simple and incredibly powerful, the curved arrow. You can think of it as the grammar for the language of chemistry. Once you can read the arrows, you can understand the story of pretty much any reaction.
Okay, let's break this down. Every single curved arrow tells a very precise story in 3 parts. Part 1 is the tail of the arrow, the origin. It always starts at the exact spot where a pair of electrons is hanging out. Part 2 is the pathway, just the curve of the arrow itself. In part 3, the head of the arrow is the destination, the specific place where that electron pair is about to end up. So it's always from origin to destination. Simple, right?
But, and this is a big but, not all arrows are the same. There are 2 main types that you absolutely need to know. There's the standard double-headed arrow we've been looking at, and then there's this single-barbed arrow, which chemists have nicknamed the fishhook. They might look kind of similar, but what they describe are 2 totally different events.
And this shows the difference perfectly. The double-headed arrow on the left is always for the movement of a pair of electrons, 2 of them moving as a team. This is what you see when new bonds form or you create charged ions. The fishhook on the right, though, shows the movement of just a single electron. This happens a lot when a bond splits right down the middle, like you see here with chloromethane. The bond snaps, 1 electron goes with the methyl group, 1 goes with the chlorine, and you get these 2 super reactive things called radicals. Radicals are unstable because they have this lonely unpaired electron, so they're desperate to react with just about anything. The main takeaway is this: 2 barbs, 2 electrons. 1 barb, 1 electron. Got it? Okay, so we know what the arrows mean. Now let's look at the 3 most common moves an electron pair, using our double-headed arrow, is going to make. First, electrons from a double or triple bond, what we call a pi bond, can just shift over to form a new bond right next door. Second, those same electrons from a pi bond can just jump completely onto a nearby atom, which usually gives that atom a negative charge. And third, a lone pair of electrons just sitting on an atom can swing in to form a new bond. Seriously, these 3 pathways cover a massive amount of organic chemistry.
So we've spent all this time on the how electrons move and how we draw these cool arrows. But that just leads to the biggest question of them all, doesn't it? Why do they move in the first place? What's the invisible force actually pushing and pulling these electrons around?
Well, the answer comes down to something we call electron displacement effects. And as this little flowchart shows, these effects come in 2 main flavors. You've got temporary ones, which only kick in when a molecule is actually being attacked by another chemical. But even more important are the permanent, ground state effects. These are imbalances that are just built right into the molecule's structure from the get-go. For the rest of our time here, we're going to focus on one of the most critical ones, the inductive effect.
The whole thing starts with a concept called electronegativity. It's basically just a measure of how greedy an atom is for electrons. So when you have a carbon atom bonded to a super greedy atom like chlorine, they don't share their electrons equally. It's like a game of tug-of-war, and the chlorine pulls that electron cloud towards itself. This creates what's called a polar covalent bond, leaving the carbon with a little positive charge, we call that delta plus, and the chlorine with a little negative charge, or delta minus. And that imbalance, that's the engine for everything.
Now, what's really cool is that this one polar bond doesn't just exist by itself. Its effect can actually be felt by its neighbors, creating this sort of domino effect, or a ripple, that travels right through the molecule's skeleton. And that transmission of polarity is exactly what we call the inductive effect.
Let's watch exactly how this ripple happens. In step 1, that super greedy chlorine atom yanks the electron density towards it. That gives the first carbon, C1, a partial positive charge, R delta plus.
Now, because C1 is a little bit electron poor, what does it do? It tries to make up for it by tugging on the electrons it shares with its neighbor, C2. And that's step 2. The result? C2 now gets an even smaller partial positive charge, which we write as delta delta plus. You see how the effect is being passed down the chain? It's like an echo.
But, and this is a really crucial point, this ripple doesn't go on forever. It fades out. Take a look at this molecule here. The bromine creates a strong delta plus on that first carbon. That induces a much weaker delta delta plus on the second one and an almost non-existent delta 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 plus on the third. The key takeaway here is pretty simple. After about 3 bonds, the inductive effect has basically vanished. It just peters out. We call this attenuation. Now, of course, different groups you can attach to a carbon chain have different effects. We basically classify them all relative to hydrogen, which we treat as our neutral baseline, our 0 point. On one side, you have the electron withdrawing groups, which have a negative I effect. These are the greedy ones, like halogens or nitro groups, that pull electron density towards themselves. On the other side, you've got the electron donating groups, with a positive I effect. These are usually your alkyl groups, like methyl, that are less greedy than carbon and actually push electron density away. Okay, so we've learned the language of arrows, and we've learned about the force behind the inductive effect. Now it's time for the big payoff. Let's put it all together and see how this lets us read a molecule and actually predict what it's going to do. And this slide says it all, really. That permanent landscape of delta plus and delta minus spots created by the inductive effect, it's literally a roadmap for reactions. It screams to other molecules, hey, over here is an electron-poor spot, and over here is an electron-rich spot. So when another chemical comes along that's rich in electrons, something we call a nucleophile, or a nucleus lover, its approach is at random. No way. It is naturally and powerfully drawn straight to that electron-deficient delta plus carbon. The inductive effect has literally painted a bullseye on the molecule. So let's just quickly recap the big ideas. First, curved arrows are the language we use to draw the story of electron movement. Second, the inductive effect is this permanent, built-in polarity that's caused by differences in how greedy atoms are for electrons. Third, this effect travels down the carbon chain, but it fades out pretty fast. And finally, and this is the most important part, this built-in polarity creates a roadmap that lets us predict where chemical reactions are going to happen. You've basically just learned how to see the invisible architecture that runs the entire chemical world. You can now look at a molecule and see not just some static drawing, but a dynamic map of forces and possibilities. It's kind of a superpower, right? So the only question left is, with this new vision, what are you going to want to explore next?